Welcome to the Deep Dive, where we take the most complex, source-heavy subjects and distill them down to the foundational knowledge you need.
And today, we are undertaking a monumental task.
We really are. We're decoding a single person whose influence is so pervasive, so fundamental to modern computing, that he essentially gave the field its mathematical rigor, its academic structure, and even the beautiful fonts it uses to publish its findings.
Our deep dive is into Donald Knuth, the professor emeritus at Stanford. He's a figure whose sheer scope of work spans pure mathematics, the bedrock of software engineering, and the highly technical world of typography.
He's really the original polymath of the digital age.
He really is.
Okay, so let's unpack this. Knuth has rightly been called the father of the analysis of algorithms, a title he earned through decades of work on his opus, The Art of Computer Programming, or TAOCP. But that is just the beginning.
Oh, absolutely. And it's crucial to establish his prestige right away. He's the 1974 recipient of the ACM Turing Award.
Which is basically the Nobel Prize of Computer Science.
Exactly. And you don't get that award for just being a good programmer. It's reserved for people who fundamentally changed how the discipline thinks about itself, its goals, and its methods.
And our mission today is pretty complex. We're moving beyond just a standard biography. We want to dive deep into the actual systems he created.
Right. We have to explore TAOCP, the text typesetting engine, the underlying METAFONT language, and his philosophy of literate programming.
We'll also get into some of the technical innovations that sometimes get overlooked, like the Knuth-Morris-Pratt algorithm.
And his really abstract mathematical work, like Knuth's up-arrow notation, which deals with numbers so huge they almost defy description. It's a staggering legacy, and we need to understand not just the what, but the why it all matters.
So to understand how one person can achieve this level of mastery over a brand new scientific field, you have to look for the early signs.
You do.
And Knuth's story starts with a fantastic anecdote from his childhood that just perfectly illustrates his whole approach to problem solving.
The ability to treat a totally everyday puzzle with complete mathematical and linguistic rigor. It was there almost from the start. So Donald Knuth was born in 1938 in Milwaukee, Wisconsin.
And his father had a small printing business and taught bookkeeping.
Two professions that rely on painstaking precision. It's a very telling detail, given where Knuth ended up.
It really is. And this famous anecdote, it's from when he was only in 8th grade, and it involves a promotional contest for the Ziegler giant bar.
Not computer science, just a word puzzle. But it's where he first showed this exhaustive commitment to completeness.
So the challenge was pretty simple.
Yeah, find the maximum number of unique words you could form by rearranging the letters in the phrase Ziegler giant bar. The judges, they announced they'd found about 2,500 words, and that was the benchmark.
But Knuth sees this not as a word game, but as a problem of permutations constrained by the English language. So he decides to apply this just at an absolutely uncompromising level of analysis.
He does, and he delightfully fakes a stomachache to get some time off from school. And then he gets to work with an unabridged dictionary.
The methodology is everything here.
It is. He systematically checks every single word entry in the dictionary to see if it could be formed using only the available letters. This rigorous, rule-based approach, treating the dictionary as his definitive data set, that's a pure algorithmic mindset in action.
And the outcome was just astonishing.
His method identified over 4,500 words.
Nearly double what the judges found.
And that dedication paid off. I mean, he won the contest, and the prizes included a new television for his school.
And enough candy bars for all his schoolmates.
Enough for every single one. It's the perfect origin story for a man who would dedicate his life to formalizing these exhaustive, perfect computational methods.
And this methodical nature, it carried right into his higher education. In 1956, he starts at the Case Institute of Technology, now Case Western.
On a physics scholarship initially.
That trajectory changed fast when he ran into an early computer.
That was the IBM 650. And like a lot of pioneers, he didn't just see a tool. He saw an inefficient system. He gets his hands on the manual, and instead of just learning how to use it, he reads the assembly and compiler code and decides,
I can do better.
I can do better. I mean, the confidence for a young student to not only understand the system architecture, but to immediately decide to rewrite the core code to make it more efficient.
It's incredible.
It really speaks to an immediate, profound understanding of the logic. And this insight quickly found its way into some surprisingly public applications.
Hmm.
In 1958, he developed one of the earliest known examples of predictive analytics in sports.
The basketball program,
Yeah.
yes. He created a program to help the school's basketball team strategize. What he did was he basically assigned quantitative values to players, using data to estimate scoring probability and inform strategy.
At a time when coaching was all intuition.
Exactly. Using data analysis to dictate player roles was almost unheard of.
So was it seen as heresy by the traditional coaches, or was it embraced because it actually worked? Well, the success is what got the attention. This kind of data-driven modeling, which we now call the quant era, was so unusual in the late 50s that it got national media coverage.
Wow.
Newsweek and the CBS Evening News both reported on this college student using a machine to help his team win.
So that really cemented his path away from physics.
Absolutely. He switched to mathematics, and his performance was so outstanding that in 1960, the faculty gave him this special award that let him receive both a Bachelor of Science and a Master of Science degree at the same time.
Then he moves on to Caltech, gets his PhD in math in '63.
And his thesis was on finite semifields and projective planes.
What does that tell us about his foundational interests?
It shows he was grounded in extremely rigorous abstract math. Projective plane semifields, they deal with structures and geometries, connecting pure algebra with combinatorial structures. It's highly abstract stuff.
So he had the intellectual horsepower not just to program algorithms, but to understand the deep structural math that underpins all computation?
It was the perfect theoretical base for someone who could later formalize the structure of programming itself.
Okay, now let's talk about his early career choices, because they show this really unusual dedication to the craft over the cash.
His priorities were definitely not standard. While he was still a graduate student, he was consulting for Burroughs Corporation, writing an AlGOL compiler for the B205. This hands-on, deeply technical work was his priority.
So much so that he was willing to turn down major financial opportunities.
Yes. The sources say he rejected a $100,000 contract from Green Tree Corporation to write compilers.
And prestigious academic honors, too.
He did. He turned down a National Science Foundation fellowship and a Woodrow Wilson Foundation fellowship because accepting them would have meant he had to stop his consulting work with Burroughs.
He literally chose complex problem-solving over immense financial security or academic prestige.
The choice highlights a critical difference, you know. He wasn't optimizing for income or status. He was optimizing for the quality and depth of the work itself.
And that depth showed up in his consulting between 1960 and 1968.
For sure. He was working on the B220 AlGOL compiler, and he suggested this key extension to the symbol table, letting one symbol stand for a whole string of symbols.
This became the basis of the define function in Burroughs' LGOL, right? A feature that a lot of other languages adopted.
It did. But here's a fascinating point of technical friction.
Got it.
Didn't this innovation initially cause issues with other foundational figures, like Edsger Dijkstra?
It did. It's a wonderful example of the philosophical battles that shaped early computing. Dijkstra, who was a huge proponent of clean, structured programming, he initially saw the define function as a source of complexity
He called it a terrible idea.
because it obscured the clean structure of the code. So even creating what we now see as standard compiler features was up for intense debate among the field's founders.
Exactly. It shows that even seemingly small technical nuances, like defining a macro, were revolutionary enough to generate this intellectual conflict that ended up defining language syntax for decades.
So his consulting wasn't just writing compilers, he was actively shaping the tools and the philosophy of this whole new field.
And he was also involved in early simulation languages, which kind of paved the way for object-oriented design.
Right, he co-designed SOL, the simulation-oriented language.
Correct. But even more telling, after he went to a conference in Norway in 1967, he was so impressed by Simula, which is historically seen as the first object-oriented language, that he immediately pushed Burroughs to adopt it. He was a consultant dedicated to advancing the state of the art.
This whole period of deep, applied industry work created the perfect storm of experience and rigor that led him to his true life's mission.
Writing the master text.
Exactly.
That industry pivot is essential because it was industry that commissioned the work. In 1962, Knuth accepted a commission from the publisher Addison Wesley.
To write a single book on compilers.
A single book.
He set out to write a manual, and he ended up writing the intellectual foundation for an entire scientific discipline. How did that happen?
The initial scope it became insufficient almost immediately. While he was working on it, Knuth realized he couldn't possibly explain advanced topics like compilers without first establishing a complete and fundamental theory of computer programming itself.
Because it didn't exist yet.
It didn't. The existing body of work was too fragmented and, frankly, often incorrect.
So the project just exploded. One book became what he initially thought would be 6 volumes, and now he thinks it'll need 7.
All dedicated to comprehensively cataloging the entire subject. Volume 1 was finally published in 1968.
This was less a publishing decision and more an intellectual necessity then.
Absolutely. Knuth felt compelled to correct the narrative. He described computer science in the 1970s as a totally new field with no real identity, and he said that a lot of the papers coming out were quite simply wrong.
That is just astonishing. The field was literally lacking fundamental rigor until he came along and provided it.
So his core motivation was to put straight a story that had been very badly told. He was looking for mathematical rigor, proven correctness, and deep analysis, where before there was just guesswork, trial and error, or inefficient hacks.
So if he corrected the field, what specific tools or terms did he invent or formalize that we still use today?
This is the real crux of his contribution. Based on the material he compiled for TAOCP, Knuth decided the proper name for his work, and maybe for the field itself, was the analysis of algorithms. He formalized the mathematical techniques for evaluating the efficiency of computational processes.
This leads us straight to asymptotic notation, or big O. We hear this term everywhere in computer science today, but what was the revolutionary insight at the time?
Well, before Knuth, if you want to know which of two algorithms was faster, you often had to, implement both and run them on a specific machine with a specific data set.
And the results would depend on all those factors.
Highly dependent on implementation details, programming language, hardware, everything. Knuth standardized a mathematical way to compare algorithms independent of all those factors.
So big O notation, which he popularized, doesn't tell you how long an algorithm will take in seconds, but how its running time or memory usage scales as the input size grows.
Precisely. It describes the growth rate. A quick analogy. Imagine you're searching for a name in a phone book. If the phone book has n names, you might spend a constant amount of time, say 3 seconds, to find the right page. That's O1, constant time.
Right.
But if you have to sort the entire phone book first, the time required grows much faster, maybe O(n) log n. Knuth gave us the language and the mathematical proof to analyze and compare these fundamental growth rates. It made algorithm analysis a rigorous science.
It's the metric by which we judge the quality of all code. But to make sure the lessons in TAOCP were pure and machine independent, he made a very specific and maybe controversial choice about the language he used.
This is a detail that shows his dedication to pedagogical purity. Instead of writing his algorithms in a high-level language like Fortran or Algol, which were always changing,
He wrote them in an artificial abstract assembly language of his own design, MXX and later MMIX.
he did.
Why an assembly language? That sounds immensely difficult for both him and the reader.
He believed that any high-level language would eventually become obsolete, and that would date the material. Assembly language, or machine code, is the fundamental language of the computer. It deals directly with memory and registers.
So by using an idealized assembly language, MASX, he stripped away all the confusing syntax and quirks of real-world languages.
And forced the reader to focus on the absolute core minimal operations required for the algorithm. It was an intellectual constant that wouldn't shift with compiler trends.
It's a challenging choice, but it ensures the book's permanence. The focus is strictly on the process and the mathematics, not the implementation flavor of the day.
Exactly. And the ongoing nature of this project is maybe the most incredible testament to its importance. Knuth has dedicated his life to finishing this series. In 1992, he took the radical step of temporarily retiring from regular teaching and research at Stanford,
The equivalent of stepping away at the height of your career.
to specifically focus on finishing TAOCP.
30 years later, where does this sprawling project stand?
It's still a multi-decade marathon, constantly being revised and expanded. Volume 4A came out in 2011. Volume 4B came out much more recently in October 2022, but here's the critical scale of it all. Knuth anticipates that Volume 4 alone will ultimately have at least parts A through F.
Wow.
He still has monumental work ahead just to complete Volume 4, let alone the projected Volumes 5, 6, and 7.
That magnitude. Knowing he might be in his late 80s or 90s before he completes a single volume that began 30 years ago, it's staggering. It speaks to the sheer intellectual labor and the explosion of knowledge in computer science itself.
It really does. There's an anecdote from the early 70s that shows how the scope has always been unmanageable. Knuth spent a year at the University of Oslo from 72 to 73. His original plan was to use that year to write Volume 7, which was planned to cover programming languages.
A nice, neat goal. Did he achieve
Bleh.
it?
Not even close. When he got there, he'd only finished the first 2 volumes. He ended up spending his time teaching and working feverishly on Volume 3, Sorting and Searching, which was published soon after he got back. The foundational work always demands more attention.
The prep work for TAOCP was so rigorous it basically launched its own field of mathematics, too.
That's where concrete mathematics comes in. The mathematical preliminaries for Volume 1 were so extensive that they expanded into a full, rigorous course he introduced at Stanford in 1970.
So the math required just to read the first book became a course worthy of its own textbook.
That's right, the textbook Concrete Mathematics, a foundation for computer science, which he co-authored, came directly from that course.
And linking back to the idea of what to call things, he also thought computer science was too limiting a name for the discipline he was creating.
He proposed algorithmics. He felt that computer science incorrectly implied that the field was fundamentally about the machine.
But his argument was that it's about the process.
Exactly, the study of algorithms and computation. These concepts transcend any specific hardware. While computer science stuck, his preferred name highlights that the core value of the field lies in mathematical analysis, not electrical engineering.
Okay, let's transition from the theory of algorithms to what seems like a completely different world. The technical aesthetics of publishing.
This transition is one of the most unexpected yet foundational detours in all of computer science history. Knuth basically invented modern, high-quality digital typesetting because he couldn't stand the way his own book looked.
Pure technical pragmatism born from aesthetic frustration. And the whole thing was tied directly to his masterwork, TAOCP.
In the mid-70s, the publishers of TAOCP made a technological shift. They moved away from the traditional high-quality monotype system to newer phototypesetting technology.
And the results? They were lacking.
They were dreadful, particularly for scientific notation. Knuth looked at the proofs for the new printings of his life's work and was reportedly so frustrated with the inability of the latter system to approach the quality of the old volumes that he stopped writing about algorithms entirely.
He literally hit pause on the single most important work in computer science because he didn't like the kerning and the placement of his mathematical integrals.
That is a truly beautiful level of obsessive dedication to quality.
It really is.
He saw a system failure. Existing digital systems just couldn't handle the complex requirements of mathematical documents, the precise alignment of fractions, the nesting of roots, the aesthetic consistency of symbols.
All the fine details of professional typography.
And this led to the creation of not one, but 3 interconnected systems that underpin how much of the world's academic research is published today.
Okay, let's break them down.
First, there is TeX. That's pronounced tech, rhyming with blech. This is the computer typesetting system itself. It was designed to achieve the highest possible typographical quality.
Then he realized he couldn't get that quality without controlling the fonts themselves.
Exactly. This led to METAFONT. METAFONT is a separate programming language he developed specifically for defining and rendering typefaces.
So how is METAFONT different from standard font design?
It's fundamentally algorithmic. Instead of drawing a letter form manually and then digitizing it, which can result in fixed, sometimes chunky bitmaps METAFONT describes typefaces geometrically and parametrically.
So you define the shape of the letters with math.
With mathematical rules and variables. This means the fonts can be rendered at any resolution and are perfectly consistent across different scales and weights.
So it's a programmatic way to draw letter forms with mathematical precision, ensuring they look perfect whether they're tiny footnotes or massive section titles.
And the resulting family of typefaces he created using this language is called computer modern. Together, TeX for the layout, METAFONT for the font design, and computer modern as the typeface family. It created this closed, flawless ecosystem for digital typography.
The effort was so massive it resulted in its own definitive text, right? The 5-volume set, Computers and Typesetting.
Published between 1984 and 1986. It really speaks to his immense confidence that he saw a flaw in the entire publishing industry and decided fixing it himself was a faster solution than just asking his publisher to switch vendors.
That kind of total systems design is so rare. He couldn't trust the tools, so he built them from the ground up to his own specifications. And this foundational work quickly led to the layer most modern users are familiar with.
The layer known as latex.
Right.
Text itself is powerful, but it requires a lot of low-level coding. The widely adopted macro package, latex pronounced LaTeX or LaTeX, was developed by Leslie Lamport.
Lamport, another titan of computer science, basically made text accessible to everyone else.
He provided a necessary layer of abstraction. LaTeX lets academics and users focus on the structure and content of their document chapters, sections, references, instead of the precise typesetting commands.
And he published the first user manual in 1986.
Precisely when Knuth finished publishing the source code for Text and METAFONT as books, it shows how immediately the community recognized and built upon the rigorous foundation Knuth had provided.
And text and latex are still the gold standard for high-quality mathematical and scientific publishing today, decades later. It's hard to find a better example of enduring technical achievement.
The development of Text and METAFONT wasn't just a distraction either. It was the crucible for one of Knuth's deepest philosophical contributions to software engineering, literate programming. He realized the problem wasn't just how the code ran, but how the code was understood.
This philosophy fundamentally shifts the programmer's focus. If the computer is the audience, the code is instructional. If the human is the audience, the code becomes narrative.
That is the core idea. Knuth posited that programmers should view programs as works of literature, meant to be read, understood, and appreciated by intelligent human beings. His whole mission was to say that the primary task of the programmer should be explaining to human beings what we want a computer to do. The executable code is just a secondary thing.
So, instead of writing code and then varying explanatory text and comments, the explanation and narrative around the logic become the single, unified source document.
Exactly. The human narrative dictates the structure. The standard approach writing code for the machine and then forcing an explanation around it leads to poor documentation and drift. Literate programming solves this at the source.
And to technically support this, he designed the WEP system. So how did it work? How did it turn a novel into executable code?
The brilliance of the WEB system is its dual-purpose source file. That single file contains both the human-readable narrative and the fragments of executable code. The source is then processed in two distinct opposite ways.
The first way is for human readers.
That's the weaving process. The weaver reads the WEB source, extracts the narrative and the beautifully formatted code segments, and produces a text file. That generates a descriptive, readable, and perfectly typeset document. The documentation flow.
And the second way is for the machine.
That is the tangling process. The tangler reads the very same WEB source file, but it ignores the narrative. It extracts only the code fragments and arranges them in the specific order needed for execution. It produces an executable source file, originally Pascal, which is then compiled into a binary.
That is so elegant, because it guarantees that the documentation and the code are always synchronized. If you change the code, you have to change the narrative in that single source file. There's no documentation drift.
And Knuth used the system himself to program both Text and METAFONT, publishing the source code as books, which served as definitive examples of literate programming in action. The approach has proven resilient, too. A later version, CWEB, replaced Pascal with C, C++I, and Java.
It's a methodology born directly out of his insistence on clarity and rigor, connecting right back to the ambition of TAOCP.
Absolutely. And speaking of rigor and intellectual integrity, this brings us to his highly distinguished academic career and his powerful ethical stance on innovation.
He joined the Stanford faculty in 1969, but the university recognized his unique stature by creating a one-of-a-kind title just for him.
They did. In 1990, he was awarded the academic title Professor of the Art of Computer Programming. No one else holds this title. It acknowledges that his mission wasn't just to teach courses, but to fundamentally define the entire discipline.
He's now Professor Emeritus.
And moving to his ethics, he is famously a strong opponent of granting software patents, especially for basic programming techniques.
His opposition is rooted in his desire to foster innovation. He strongly opposes patents for what he calls trivial solutions that should be obvious.
His concern is that patenting basic conceptual building blocks of software stifles the free exchange of ideas necessary for the field to advance.
And he hasn't just written papers about this. He's taken his case directly to the relevant authorities.
He has. He's expressed his disagreement directly to the United States Patent and Trademark Office and the European Patent Organization. He sees these trivial patents as monopolies on common sense.
But his view is nuanced, right?
It is. He holds a more balanced view for truly novel and complex mathematical solutions, like the interior point method of linear programming, which required immense intellectual effort. He wants to protect true invention while keeping basic tools free for everyone.
That's a principled stand that defines him not just as a creator of code, but as a steward of the discipline.
And despite the intensely serious nature of his work, Knuth has this famous sense of humor and a unique way of connecting with the community, often using mathematically precise satire.
Let's start with the tradition every computer science student knows.
Okay.
The unique system he established for rewarding people who found errors in his published works. The Knuth reward checks.
The famous finder's fee. Knuth made it a practice to pay $2.56 for any typographical errors or mistakes found in his books, and he offered $0.32 for valuable suggestions that led to minor improvements.
Why that very specific, mathematically unusual number, $2.56?
Because, as he explained, 256 pennies is one hexadecimal dollar. 2 to the power of 8. It's a perfect confluence of technical precision, number theory, and cleverness. It's a literal representation of his worldview.
And these checks are far more valuable as trophies than as currency.
Oh, absolutely. Technology Review called these checks among computerdom's most prized trophies. They're a badge of honor, proof that you rigorously analyzed the master's work and found a verifiable flaw.
But the system had to change.
Because of bank fraud, yes. He stopped issuing real negotiable checks in 2008. But being Knuth, the solution was technical and whimsical. He now issues error finders a certificate of deposit from his own fictitious Bank of Sans Serif.
So the tradition continues, just with a layer of literary satire. Sans Serif being that fictional island nation from an April Fool's Day joke.
Exactly. And speaking of satire, we have to mention his earliest published work, which was far from TAOCP.
His very first scientific article was actually a piece of humor in Mad magazine, way back in June 1957.
Mad magazine. That tells you he has a deep-seated appreciation for systematic absurdity.
What was the article?
It was titled The Potsdam System of Weights and Measures. It systematically defined a new, internally consistent but utterly ridiculous measurement system. For example, the fundamental unit of length was the thickness of Mad Magazine issue number 26.
And the unit of force.
It was named What Me Worry, after the magazine's mascot, Alfred E. Neumann.
That just shows he can apply the same rigorous structure of definition and system design to comedy as he can to computation.
His wit shows up in his technical writing, too. To illustrate recursion in the index of TAOCP, Volume 1, he intentionally created a circular definition.
Right. If you look up circular definition, or definition of circular, they just refer back to each other,
Yeah.
forcing you to recursively define the term.
And of course, the most famous quote associated with him, the caution against the gap between theoretical proof and practical execution.
Beware of bugs in the above code. I've only proved it correct, not tried it.
It captures the humility of a mathematician entering the messy world of engineering, acknowledging that mathematical correctness is only the first step.
Now let's bring in a highly technical detail that was promised earlier but often gets overlooked. His contribution to defining extremely large numbers, the up arrow notation.
This is where we see his pure mathematical rigor in action, extending standard mathematical tools. Knuth's up arrow notation, or hyperoperators, is a way to define rapid growth functions.
So why do we need a new notation? Doesn't standard exponential notation cover large numbers?
Standard exponential notation handles iterated multiplication. 10 to the power of 100 is 10 multiplied by itself 100 times. But what if you need to iterate exponentiation?
That's where the arrow comes in.
Exactly. One arrow is standard exponentiation, or power. 2 arrows, a double up arrow, denotes tetration, which is iterated exponentiation.
So 3 double arrow 3 would be what?
That would be $3, which is 327, a very large number. If you use 3 arrows, you'd be dealing with iterated tetration, called pentation, which produces numbers so inconceivably vast they can't even be written down using standard powers.
That's abstract math that immediately speaks to the limits of our standard notation.
And it connects directly to computer science, especially in areas like complexity theory and discrete mathematics. It just proves his ability to build necessary mathematical machinery from scratch when he needs it.
On a more personal note, his later years show a dedication to music and faith, applying that same systematic rigor to these non-technical areas.
Knuth is a devout Lutheran, and his project 3.16 Bible Texts Illuminated perfectly combines his interests. He performed a systematic study of the Bible, analyzing chapter 3, verse 16 of every single book.
Again, applying algorithmic rigor to source material.
Exactly. He's looking for patterns and structure. And the book itself is a work of high-quality typography. Each verse is rendered in beautiful calligraphic art. This whole project led to his lectures at MIT on the intersection of religion and computer science, published in things a computer scientist rarely talks about.
He also applied his structural obsession to music as an accomplished organist and composer.
Both he and his father served as organists, and his home features a large 16-rank organ. His compositional work is equally ambitious. In 2016, he completed Fantasia Apocalyptica, a massive, complex piece for organ.
And he described it as a translation of the Greek text of the Revelation of St. John the Divine into music.
It's the ultimate expression of his philosophy, taking highly complex, structured source material, whether it's a biblical text, an algorithm, whatever, and translating it into a formal, rigorous, and beautiful system. The piece premiered in Sweden in 2018.
We have to close this section with one final charming personal detail that reflects his global outlook: his Chinese name.
His Chinese name is Gao Dana. He was given the name in 1977 by Francis Yao, another prominent figure in the field, just before a 3-week trip to China.
And why did he embrace it so completely?
Knuth understood the necessity of connecting with the rapidly growing community of Chinese computer programmers. He adopted the name because he wanted to be known and recognized by them. He later noted that since 1989, his name, Gao Dina, has been placed prominently atop the header of the Journal of Computer Science and Technology in China.
That simple acknowledgement that he cared enough about the global community to adopt a formal name, it just speaks volumes.
When we synthesize Donald Knuth's career, we realize his legacy is much larger than a list of algorithms. It's the intellectual framework that established computer science as a genuine, rigorous mathematical discipline.
He didn't just participate in the computing revolution, he wrote the fundamental rule book for how to think about and measure efficiency.
He took a chaotic, fragmented, early field and imposed mathematical clarity upon it.
And the accolades reflect this. He received the first ACM Grace Murray Hopper Award in 1971, the Turing Award in 1974, the National Medal of Science in 1979, and the Kyoto Prize in 1996. He's a foreign member of the Royal Society, and for a touch of celestial recognition, there is an actual asteroid, 21656 Knuth, named in his honor.
He is, quite simply, the standard against which technical rigor is measured. He demonstrated that complexity has to be handled with systematic clarity, and that the structure of an algorithm should be as beautiful as its function is efficient.
So let's end with this final thought for you, the learner, to carry forward. Knuth made the profound decision in 1992 to dedicate the rest of his professional life to finishing the art of computer programming.
He's been working full-time on this foundational text for over 3 decades, and he still anticipates needing to publish multiple complex parts A through F just to complete Volume 4.
So, when the foundational, single-author text of a discipline requires that level of continuous, decades-long, dedicated intellectual labor just to keep pace with the knowledge,
what does that say about the sheer, sprawling, and relentless growth of computer science today? It suggests that the art of computer programming is not a fixed masterpiece, but an ever-expanding, unending canvas of complexity.
And that is something worth pondering. The unending nature of foundational knowledge. The next time you attempt to write an efficient loop or find yourself struggling to explain complex code to another human being.
Thank you for diving deep with us.
We'll see you next time.